Okay, as I said before, NIDA very good about continuing where we left off, but that is not the case in the equation I was working on. So I used some incorrect values from a previous example, thinking we had just carried it over, but we had not. This is a completely different equation, or completely different problem. So we're going to have to do it from scratch. Now we're looking just for L1 here. So that makes our life a little bit easier because when I look right here, I see just L1. So all we really have to do is get the ohmic value, the x of L of L1, and that would be 2 times pi times 10 kilohertz times 10 millihenries. Now again, not to beat a dead horse, but milli, and whoops, underlined the wrong thing there. Milli and K cancel each other out, so we don't have to take those into account. We can use simple numeric values here. So let's do that. So 2 times, and pi is 3.14, times 10 times 10 equals, and I come up with the wrong value. I think I messed up when I pressed in pi, so let's try that again. 2 times 3.14 is what I missed, times 10 times 10. We weren't very far off, but there would be a difference between 620 and 628. That would be a little more rounding than I would want to do. So the x of L1, its impedic value, or its ohmic value, not impedic value, is 628 ohms. Now to get IT, it's just a matter of, or I should say, of L1. It's a matter of dividing 10 volts by 628 ohms. So we can come over to the calculator. We can do that. 10 divided by 628 equals, and we're going to have to move that decimal place because this is true amps. If we want milliamps, which all our answers are in milliamps, we've got to move it 3 places. So we multiply it by 1,000, put the decimal point right there between the 5 and the 9, 15.9 milliamps. Because we multiplied a small number by 1,000, we broke it into 1,000 pieces, so our prefix becomes milli. So let's see if that's right. 15.9 milliamps, and absolutely it is. So moving on to the next slide here, we're going to learn about coils and resistors in parallel. So before we were just doing coils in parallel, and we can't just do what we think we might would do, and that's the product over sum, and it's not going to work. So what will? Let's see. And R and XL are not exactly the same quantity, and they oppose current differently. So we have to find their impedance, which is a Z value that's expressed in ohms. And here is the wonderful formula for that. Impedance total is R times XL over the square root of R squared plus XL squared. So you better write that one down. You're going to need it, I promise. So here's the difference between series. We just use the bottom part of that equation. In parallel, we use this equation, which has a different value on top. So we've got our denominator here is just our equation here. So we did change that up a little bit. So make sure you remember which way you're using it. Taking the square root of the sum of the square values accounts for the 90 degrees phase difference, and there is a phase difference there. So in this circuit, ZT equals 24 ohms. Now let's look at how they got that. They took the ohmic value of 30, the X of L value of 40. Up on top, they multiplied. On bottom, they squared each of those and got the square root, came up with 1,200 over the square root of 2,500. That gave us 1,200 divided by 50, which equals 24. So there's the math, and we're about probably to apply it in an equation. To get total current, we can use that impedance value and apply it. So we can take 100 volts AC, divide it by 24 ohms, which is what they're doing here. 100 volts AC, dividing it by 24 ohms, and they're getting 4.17 amps. So pretty easy there. At least that formula stays with us the same. And we can calculate branch current simply by doing the E over R or the E over X of L. You have to be careful with that second one because a lot of times students want to, and I will too, want to use the millihenry value of the coil rather than the X of L value, which is really its ohmic value. So we got to make sure that bottom number is a ohms, not a millihenry. So just be sure you do that. All right. So here we have IR of 30 ohms. We're dividing that to 100 volts. This is parallel, so this R1 is seeing 100 volts, 3.33 amps. 100 volts, and they have an error here too. They got the right outcome, but they have a wrong value. Let me fix that for you. Goodness, it's a little scary, but just remember these are humans that write these as well. So X of L1 is actually 40 ohms. And if we divide 40 into 100, we get 2.5. So let's do that on our calculator just so you can see that it works out well. 100 divided by 40 equals, and there we get 2.5 amps. So right answer, just happened to have the wrong value down here, and it happens. What they did was they popped in this value, which is our Z total, rather than the value of X of L1. It happened to all of us, just food for thought, and a good way of making sure we know what we're doing. Alright, so let's move to the next slide. So due to the phase difference, though, we can't just add those currents together and come out with total current. Oh no, couldn't be that simple. We have got to use this formula, which is I total equals the square root of IR squared plus IL squared. So again, another formula for us to apply. So we took the 3.33 that we got for the resistance current value, 2.5 that we got from the inductance. We squared both of those, added them together, got the square root of that, and came up with 4.16 amps. So here we go. Let's use an example. You will solve for total and branch currents here. So we've got some interesting little problem here. So the very first thing that they did was they took the two coils that were in parallel, and remember this is the parallel formula, and they multiplied them and did product over sum. We could have done reciprocal. In fact, I'll illustrate that just because, again, I like that one. So our two values are 66.7 and 100. So 100 reciprocal plus 66.7 reciprocal equals reciprocal. And we got 40 millihenries to, in fact, 40.01, which rounds beautifully down to 40 millihenries. So we arrived at the same answer using the product over the sum. I mean the reciprocal rather than the product over the sum. So we got 40 millihenries. Next thing they did was they came up with X of LT. So we had to take this 40 millihenries and 2 pi FL it. I know it's a weird way of saying it, but it's accurate. 6.28, which is 2 times pi, times 16 kilohertz, times 40 millihenries. Remember, these will cancel out. So 6 times 16 times 40. Let's do that math so you can actually see it on the calculator. So we'll say 2 pi, which is 6.28, times 16 times 40 equals 4,019, and they rounded that simply down to 4K. So good enough. So what's next? RT is 3K. That's simple math. 1K plus 2K, 3K. ZT, remember we got a different formula now. we have to product at the top, square each of the values on bottom, and then get the square root. So 3 times 3 is 9. And they kind of omitted a step, but I'll put it in here for you. It's something that should be apparent, but just in case you're wondering how they got to 5K. They squared 3K, which is 9K. They squared 4K, which is 16K. And I apologize for my writing. So 9K plus 16K gave us the square root of 25K. And the square root of 25K is 5K. Then they divided that into 12 mega, and that gave us 2.4K. If you want to see that in units, I'll show you. 12K, 3K times 4K is 12 meg, because if I literally do 3,000 times 4,000, I get 12 mega, because mega means million, so we're literally going 3 places, 6 places, and we're applying the M, which means times 1 million there. And then we're dividing that by 5K, so we're going to divide it by 5, 1, 2, 3, and we get 2,400 or 2.4K. So again, fairly easy math. I'm going to try to finish this one real quick. We're getting to the easier parts of it anyway, so we only got about 3 minutes left, so I'm going to try to finish at least this particular problem we're on. So now we've got an IT possibility for calculation. So 15 volts is our applied voltage. We've come up with a ZT of 2.4K, just a simple matter of doing that math. 15 divided by 2.4K, and we know our answer will be in millis because we're dividing by K, 6.25 milliamps. So that's pretty straightforward. Now we want to calculate the I of each of the values here. And we look and we divide 15 volts, which is our applied voltage, by the 3K, which is the sum of this series part of this parallel branch we have here. And 15 divided by 3K gives us 5 milliamps. I'm not going to do that on the calculator. You're welcome to. And we have to take the X of LT of what this parallel branch represents. It was 4K. 15 divided by 4K gives us 3.75 milliamps. So again, pretty straightforward. And if we apply, just as a gut check, the formula we have up here for the square root of IR squared plus IL squared to recheck this IT that we calculated, because we took just E and divided it by ZT before, we can take the individual current paths, we can square them, add them together, get the square root of that, and 6.249 is as close as you can get to 6.25 without hitting it. So pretty much works out. We know our formulas check out and we're good, so I think we're fixing to actually apply that now. That'll be the end of this video. We'll start wherever we end up next on the next video.